Electrical energy comes not only from batteries, but it also comes from power plants like Plant Hammond here that could be miles away. In our case, this is not too many miles away, but it provides electricity for many, many miles. So electrical power is what we're looking at a formula for here. Electrical power. Now, power is actually going to be measured in watts. You may remember that our light bulbs are in watts. So you probably knew that watts and electricity kind of did tie in at some point. So it looks like a very complicated formula, but actually just think of it this way. In these two here, you have different items that you have. In this case, you have the voltage and you have the resistance. You don't have the amps, but you can calculate power even if you don't have the amps. In this one, you don't have the voltage, so you can still calculate power even if you don't have the voltage. And in this one, you don't have resistance, so you can still calculate power even if you don't have the ohms or the resistance. So this just kind of makes it, even though it looks very complicated, it's not very hard to plug in because you just see what you have and what you don't. And you can end up coming up with the watts. Now, these two here kind of help find the power as it has to do with lost power. Lost power, I don't know why I'm doing it like this because I have my notepad with me here, but it has to do with lost power. And I think the term that the book uses is dissipated. Dissipated power. So in other words, you have resistance. You're not going to have, unless you have a superconductor, you're not going to have 100% of your power. You're going to have a little bit less of that. So that's what these calculate. Now, what if you do have a superconductor? This whole formula doesn't mean anything if you are using superconductors, because if you did, their resistance is zero. And if you put zero into this formula, it would, zero times anything is zero. If you were to put zero in here, it would be undefined. So it's really a moot point if you're thinking about superconductors. So you would not have any dissipated power or lost power with superconductors anyway. So these formulas work for a normal use of electricity where you do not have 100%. So let's go on to the next slide. Okay, let's use this formula to calculate some wattages. I have the formulas down here. Okay, we have what is the power when a voltage of 120 volts drives a 2 amp current through a device? So we have volts and amps. Remember, I is amp, so it's P equals I times V. P equals IV, and this should be pretty simple. I is 2 amps, and V is 120 volts. So looks like that's just a simple multiply out. 240. Now what is power in watts? Try this one. Calculate the amount of power dissipated, so you know which formulas it probably will be, by this electric heating element. If the generator's output voltage is 110 volts and the heater's resistance is 2.5 ohms. So I'll erase this. I happen to accidentally draw over that. But anyway, it already gives you which formula it is. It happens to be this one right here. So we have the volts squared. So let's first of all put the formula. P equals V squared over R. So V is 110 squared. Ooh, this might be a pretty big number. And the heater's resistance is 2.5. So let me go to my calculator element here. 110 squared. 110 Boy, I messed up right there. 110 times 110 equals 12,100. So we have 12,100 over 2.5. 12,100, see, that would be volts squared, I guess, technically, over 2.5, which probably won't be too hard to calculate. So let me go back over here. 12,100 divided by 2.5 equals 4,840. 4,840. And what would that be in? It would be in watts, of course, because that's what power's in. Now calculate the power dissipated by this dissipated by this same heater if the generator's output voltage is doubled. Okay, if voltage is doubled, that would be, instead of 110 volts, it would be 220. So let's go even more. V squared over R. And V squared now is 220 volts squared. Now, since this is squared, this should really increase the amount that is lost or dissipated, because 220 squared is going to be a lot more than 110 squared. So that's kind of the nature of this. 220 times 2, my bad, 220 times 220 equals 48,400. So we have 48,400, which is much bigger than what we had up top, volts squared, over 2.5. So that's going to be a much bigger amount of power lost, divided by 2.5 equals 19,360 watts lost. 19,360 watts lost. So notice what you have. The more volts you have, the more watts that are lost, and it's squared. I mean, here you just doubled the amount, but you did far more than just double the amount of watts that are dissipated. So that's kind of an important thing right there. Let's go to this slide. Let's talk about overloads and the danger that you have with them. When you have too many appliances, lights, things plugged in, connected across a 120 volt outlet, which is what the standard one is, the resistance of the current is lowered. So too many plug-ins means you have less resistance, and the less resistance you have, the more power is going to flow through. And when you have a circuit that has more power flowing through, it is too much power flowing through, like this definitely would have. I hope this is not actually hooked up to anything. You would have what's called an overload, which means you have a lot of volts coming through. I guess it would be a lot of amps that are actually coming through, and that is a fire hazard. Now, there were lots of pictures on the internet of fires that have burned down houses because of this, and it does burn down houses. So do not plug too many things in at once. But I just chose to show you a couple that showed the outlets burned up right there. But it can be much, much worse than that. When wire insulation wears down, like this wire here, you know, if you were to get this wire here caught up in something and the wire inside is showing, that actually happened to me not that long ago. I guess it was like last year. We had something get caught up in a wire, get caught up in a chair, and the chair was sat on it, and so this was cut. So that's also a fire hazard. Here's why: because it is a short circuit. A short circuit literally is where it does not go the complete circuit. And when it does not go the complete circuit, you have a lot of electricity, a lot of ions in a smaller place. So if you have this and it gets cut, literally, let's see what color might be a good color for this. I'll try green. Literally, you have the ions coming this way. If it gets cut right here and these wires touch, then the circuit stops here and goes back in. And whatever appliance you have out here is not going to work. And that happens with us. Whenever we had the thing we plugged in, it did not work because the circuit was cut short. The wires touched and that completed the circuit back there. And that meant you had more electricity for a smaller area. The same thing right here. You have the plastic that is cut, and here you have a wire that has started to cut. Now I don't see this one cut right here, but if it were also cut and the wires were to touch, then you've got electricity coming in one way and the circuit is cut short. It's a short circuit, and short circuits are fire hazards also. It's a great increase in current and can be very dangerous. Now, of course, here you do not have a ground wire. Notice this is a 2-plug outlet. The ones that have the 3-plug outlets, I know this is a 3-plug outlet and it burned out, but still, they are safer than a 2-plugged outlet. So grounded wire does greatly reduce the risk of electric shock from a short circuit and kind of reduces the risk of a fire as well. But if you get something like this, you do not need to plug these in. You just need to throw them away. You just do not need to plug these in anymore. So to prevent problems with overloads and to prevent problems with short circuits, humans have come up with a couple of things. Fuses. Because, for example, overloads can happen accidentally. I mean, sure, you can probably prevent some of them by not plugging things up as much on one thing. And there's also the concept of circuit breakers that helps with this also. Fuses, let's go with it first. Fuses are connected in series along the path. So if you have a fuse here, you have the electrons coming in. Let's use a better color. You have the ions coming in. It goes through here and it goes around to complete the circuit in whatever electrical outlet you have. So what happens is a fuse is a ribbon of wire, very small wire in here with a low melting point. So if you do start having too much electricity, it will melt this wire, and what it will then do is it will break. So you have an open circuit then, and the electrons are not flowing. So what that does is, that's not a bad thing. That keeps it from overloading and from preventing a fire. Is what that does. So in here, when you have these little bitty wires here, they are meant to break when you have too much going through them. Now you'll have fuses in your car also. This one looks like one that you would have in your car or in your boat. And it's happened to us one time. We had a fuse that blew and our lights would not come on. So we had to pull over and get it fixed right then, and that kept us from having an overload. So fuses, I'll go back to my script. Fuses are meant to blow out at designated levels. Like, for example, 20 amps or 30 amps or whatever the manufacturer deems as a good designated level. So if the fuse blows, you have an overload or a short circuit. Let's talk about these circuit breakers. Chances are good you have a circuit breaker in your house. Have a box right here like in your closet. These are magnetic or bimetallic strips that opens the circuit when too much current flows. Now what will happen is it doesn't break it, but it opens it up. Here you have these switches. They are all pointing this direction. They are all pointing this direction. So when you get too much electricity, suddenly one will flip back over, and all the stuff will go out that is connected to that fuse. So what you have to do is just come in and flip it right and make sure things are turned off. So chances are good you have that, and it keeps you from having to replace fuses. Hope you learned a little bit.